Hey everyone, in this video we'll see how to make the animation you're watching right now on the screen. It is a approximation of pi using the Monte Carlo method. So this will be a detailed step-by-step tutorial on how to make this code right here, to make this plot. I've put in the background some nature music, so sit back, enjoy the video, and let's go. Suppose you have a circle on top of a square, and I throw dots over it. This might sound a bit familiar to you, since it's called the dart games, if you didn't know. Now, the question is, if I throw a random dot on that board, what is the probability of hitting the circle? Now, feel free to pause the video and work it out yourself. Alright, so if you found 0.7854, then you got it. Congrats. Now, the traditional way to calculate this probability is to simply divide the desired outcome over all the possible outcomes. In our case, the desired outcome is in a way related to the surface of the circle over the surface of our square. By simplifying and rearranging, we get pi over 4. But what if, we were living before 250 BC, where pi wasn't associated with the digits 3.14, 15, etc.? Is there a way to reverse engineer this? And instead of computing the probability using pi, we compute pi using probability. Sounds crazy, right? In fact, it is very easy. All you have to do is to throw random points at the board, count the number of points inside the circle, and divide it by the total number of points. Multiply it by 4, and that's literally it. But it's seemingly random, gives us a close approximation of pi. Now we did it for a couple hundred dots. Let's actually try and make the animation we saw in the beginning of the video using Python and simulate it up to, let's say, 1 million dots and see what we get. Right, so back in Python we go. Alright, so here we are in our Visual Studio Code interface. I've created a file called estimatingpi.py. Let me actually hide this. And with all recent Python files, we begin with a import numpy as np. Then the next thing we do is define our number of samples, which is equal to a np.aRange from 1 all the way to 1000. So this will create an array containing 1, then 2, 3, 4, 5, all the way up to 1000. So it's an array of integers. Alright. We set a counter to 0. So this pi counter will designate the number of dots within the circle. And then we do a for loop. So for n in number of samples. We define the coordinates of our dot, for example, with a x is equal to np.random.uniform from -1 to 1. And then same goes for y, like this. This will create a random number uniformly between -1 and 1. And then we want to check if the coordinates of this dot is within the circle by doing an if statement. So if np.sqrt of x squared plus y squared is lower or equal than 1. So here in this case, 1 represents the radius, so from -r to r. You can also choose from -2 to 2. And here this will be also 2, but we chose 1. If the point is within the circle, we are going to increment our pi counter. So pi counter is equal to +1. And then we estimate the probability. So probability is equal to pi counter, and I'm missing an n. So n, n, and n over the number of samples. Now what this means is that this represents the number of dots within the circle, whereas n represents the overall number of dots we throw at the square, for instance. Okay. And then we can basically print the 4 times the probability. And by running our code, we will see these values. So we are oscillating around 3.1 roughly, let's say. There is a way to actually make this print a lot more visually pleasing. Now let me get rid of that. Let me define a approx pi variable here, which is equal to 4 times the probability. Since this will be pi over 4, if you multiply it by 4, it will be equal to roughly pi. Now let me import the time module, like so. And let me copy this print statement from my second screen, like so. What this does is we are doing a formatted print statement displaying the number of samples, the approximated value of pi, which is the same as this one, and we're displaying the error. A classical way of computing the error is the approximate value minus the absolute one divided by the absolute value times 100 to display a percentage. Now, this n equals /r is a carriage return character. So basically this means that the next print statement will override the current line of output rather than starting a new line. And if we add a little time delay between each print statements, for example of 1 milliseconds, we will see the following. We see that for 100, 200 samples, we are pretty close to pi, oscillating between the values of 1 and then a bit lower and then a bit more, with a 2% error. Now this is fairly good for 1000 sample. Let's actually go for 10,000 and let our code run and see what we will get. So I sped this around 10 times, so you don't have to actually wait 2 minutes watching this evolution. So we can see that already at 4,000 samples, we are oscillating around 3.1415 with a less than 0.2% error, which is pretty satisfying, the least for engineers. Let me actually stop this code right here. Now, let's try to actually utilize matplotlib to actually see what is happening. I will import the matplotlib module, so import matplotlib.pyplot as plt. And we will construct the plot we saw in the beginning of the video. I will define it in a function so that we can later on reduce the size of it. So construction. We will define a figure and an axis with the plt subplots for 1, 2. So this will generate 2 horizontal plots with a fig size, let's say, of 10 in width and 5 in height. Alright, so let me actually copy this to make it a bit faster, like so. The first one, so the axis 0 is actually the generated dots we will display, whereas this one is the curve of the approximation of pi with the number of samples. So here we set the title to random generated dots. We set the aspect ratio to equal. This is very important to get the square circle shape we want. Setting the limits to -1 and 1, so this represents the radius once again. And then here we do the same for the other plot, approximating pi, setting the limits. Let me decrease that, for instance. Let me make it 1000. And setting the y limit. And doing a grid for more visual pleasing plots. Let me return here axis. And let me call the function, so plot construction, and do a plt.show. So we can see what we just made. Let me run the code. And we can see that here we constructed our two plots. Here we will display the curve of the evolution of the approximated value of pi with the number of samples, whereas here we will display the number of generated dots. Alright, so let me close this and let me end this file. Alright, so let's put this plt.show all the way down here at the end, and let's get rid of this print statement. And let's get rid of this time module. We will not use it anymore. Alright, so the next step is actually to store the data so we can each time plot it. Let me come back here. After defining our counter, I'll be here defining a dots x is equal to an empty array and the dots y is equal to an empty array. Now, why are we doing this separately and not doing an array of dots, one single array? We will see that a bit later on. We define an array of dots color which is equal to an empty array. So this will say whether a dot within a circle is red or outside a circle is blue. And we will define a pi array is equal to an empty array. So this pi array will contain all the approximated values of pi. Now here we append these values, so dots x dot append x. Same goes for y, like so. Alright, now here we are checking if a dot is within a circle. Now naturally, if it's within a circle, we will append to our dots color array the color red, not capitalized, in lowercase. Now if it's not within the circle, we want it to be the blue color. So I'll do here dots color dot append blue. Alright, and then here, once we computed the approximate value of pi, we are going to append it to this array right here. So let me copy this and do a pi array dot append approximate value of pi. Alright, now that we stored all the data, the next step is actually to update the plots. So let's go back in our for loop right after appending the pi array. We're going to do a axis 0 dot scatter because it's dots x and dots y. So this is the reason why we separated these two instead of joining one array of dots to make it easier to plot it. So that's the single reason I came up with. And then colors is equal to dots color, and we can add a marker which is equal to a O and the size of 5. Now you can change this as much as you want, whether you want something else, for example X or I don't know, but I'll keep it as an O. So what is happening right here? When you have a dot that is within a circle, its color will be red. Respectively, if it is outside the circle, it will be blue. Alright, let's go, and when it comes to the title, let me actually copy this and paste it here. We set the title to the number of dots, red number of dots, and the blue number of dots, which are pi counter, and the rest, which is n minus pi counter, represent the blue dots, which are outside the circle. Now, same goes for the other plots, so axis 1 dot plot range 1 and then n plus 1. We want to display all the current samples we just computed, and the pi array in black. Alright, and again let me copy this axis title right here, approximate pi. Set title, approximating pi, and the value of pi. This is a formatted title, by the way. Alright, this is all we need to do. All there is left is to add a draw function, like so, and a plt dot pause with a, let's say, 10 milliseconds each time. We run our code, and we will see that slowly but surely we are successfully drawing a number of dots, approximating on the right the current approximation of pi, which is displayed here every time, the overall number of blue and red dots, so we have here the red dots and the blue dots. This is the main purpose of this video. Now you may notice that it is a bit slow. It might lag a little bit. Reason for that is at each iteration here, we are updating the title and the plot for both cases. Now one way to make it a bit faster is to actually copy this function right here. Let me exit the code right here. Alright, so let me copy this line of code right here. At the beginning, we will define a new variable called scatter, which is equal to this one. We will define it after defining our arrays right here. We will do the same thing with this one right here, but we will call it plot, for example. Then here this will be an empty array. Alright. And then instead of updating each time this part right here, so let me add a comment updating the plots. What we will do is update each 100 step. One way to do so is to simply do an if statement. If modulo of n 100 is equal to 0. So this basically means whenever n is equal to 100, 200, 300, etc. we will shift all of this. And then instead of drawing every time, we will do a scatter dot set of sets np dot column stack x and dots y. We update as well the color, scatters dot set face colors to the dots color array we have, right? And then the title we update it like the usual way. And we can update this second plot with this one together, or we can do something even better, that if modulo of n is of 2000 is equal to 0, only then we will set again the limits. So let me get rid of that. Okay. What we will do here just before is make a plot dot set data of range 1 n plus 1, then pi array. Okay, and we will do a plot dot set color to black. Alright, so is this defined here? Let's see. Yes. Alright, and then here, let's go. Right, so here we reset the axis limit. So each time we pass at 2000, we increase the limit by 2000, so we don't have to do it each time. And then we reset the axis limit to this approx pi, like so. Let me just replace all of that. So what this basically means, we are setting the y limit, where the lower value is the approximation minus a tiny amount, and the upper value is the same approximation plus a tiny amount. So in a way, we are trying to enclose the approximated value and to very zoom on it. And we set the title. Now, bear with me, it's almost done. We just have to run our code, and the magic will happen. We got an error. list has no attribute set data. So here, yes, here, this returns actually a list. We only need the first element. We rerun the code, and you'll see that it is much, much faster. Now, after each 2000 values, it updates. Like you see here, it's 4000, and then when we reach 6000, it will update again. Here, the problem with this is that the title will only update when you update the plot, but you gain a lot of time of the simulation, so it has its advantages. Now it is a bit slower because I am recording at the same time and it kind of is killing my PC, but you can see the overall, we achieved our challenge of simulating and estimating the number of pi. Here I increased it to 100,000 samples, and we'll see that after reaching the 2000 number of samples, it updates, and my PC is just dying. Alright, so let me close it there.
Hey, thank you for watching this video till this point. Consider leaving a like or subscribing. This motivates me tremendously to do even better. Check out my other videos if you liked this one. I got some Python tutorials, but also educational math. Hope to see you on the next video, and peace!